तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We are looking into the Verilog coding of multiplier algorithm, and we are multiplying two numbers of 11 bit and 8 bit, say n1 and n2, and we have also seen the definition of the various IOs here of the module mult 11s by 8s, and we have also seen the wire listing here, and right up to this we are looking into, and different wire and reg declarations. And so this far I think we had gone last time, and so these are all for subsequent stages, say reg 2, then reg 3 are all on clock 2 and 3, and all of which are naturally the signals would be a register, because we use in always block. And to start with, the final result will be here in 19 bits, and last bit will be signed. And here this we have a combination circuit to start with. What we are going to do is, as mentioned before, we will be going to remove only the magnitude of the two numbers n1 and n2 here, but in this two blocks. So whenever n1 changes from one value to another, then only we take this value. Now here what it says is, if n1 10, which happens to be the sign bit, is 0, that implies it is a positive number. So what all we have to do is just take the n1 as such and call it as n1 magnitude. So this is this means n1 number is in magnitude form. So is the case for n2 magnitude, which is basically the same here. And otherwise, that is if MSB is, that is sign bit is 1, and else will get applied, in which case what we do is take the 2's complement. This is nothing but 2's complement. We have already seen we can get magnitude merely by taking 2's complement, and that is what is here, and that is how we are extracting the magnitude of the two numbers and then applying the algorithm hereafter. And now, and these are all basically combinational circuits, and this is also another combination statement, wherein what we do is we are inspecting whether n1 and n2 are zeros. Even if 1 is a 0, final result is going to be 0, and you may encounter, if you do not take this one, you may get into problem later on with a finite fixed point arithmetic which you are dealing with. and note that all our arithmetic circuits that we have used so far, including this multiplier and adder, will be fixed point arithmetic and not a floating point arithmetic, because floating point arithmetic is more complex and would take more chip area, and this is enough for our precision, and hence we use only fixed point arithmetic. And this particular statement evaluates whether it is a 0 or not. If it is the result is 0, this will be 1. That is what this statement means. See, if n1 is 0 or if n2 is 0, then 1 is put into this signal here, and this is an wire there. And similarly, we evaluate P1. We mentioned before we had readily taken in our algorithm P1 through P8, but how do we get this? So we had to look into this. So what in the earlier example what we saw is we inspected the n2 number, and let us say MSB we take, this happens to be 0 bit. With the if we inspect that particular bit, if it is a 0, the partial product will all be 0, that all the bits will be 0 pertaining to P1, which is nothing other than n1. And if it is 1, so the final partial product will be same as n1. Whatever is the n1 number, you will get exactly the same thing. So in one case it will be all of them zeros, in other case it will be the duplication of this number. So either this number is got or a 0 is got. This can be easily evaluated by merely ANDing each of these bits, which is concatenated. For example, we have taken the n2 bit LSB alone, we are replicating, I mean rather 11 times we are duplicating, I mean it is not duplicate. So we are repeating it 11 times totally, and each of these bits are ANDed with each of the bits of n1 number. So naturally, if you AND, even if there is a 1 0 at any point place, so that particular bit will be forced to 0. So that is how you get 0. If here it happens to, if one bit is 0, all 11 bits will be 0, because it is concatenation of all the same bits. So if it is 0, the first bit of n2 is 0, naturally the final result must be 0 for all the bits, that is what is here. If it is 1, all will be 1 here, and therefore you will get exactly the n1 repeated and copied onto assigned to the P1. So is the case for all the partial products P1 through P8 here, and that is what is shown there. So now starts the first pipeline, and when positive edge of clock is encountered, this is the first pipeline register, clock 1, and what we need to do is the partial products which we have got in using assign statements earlier, we will assign it to registers. So this is the pipeline register actually here. So at every point of time, every clock you will see a register within always block at positive edge clock, and whatever comes within the positive edge clock always block, all will be registers, and that is the reason why I have given a nomenclature like this. And 1 stands for the first clock 1, so that you can readily find out to which stage a particular signal belongs to. And these are all the partial products that we had using assign statements, that we will transfer it to reg 1 when clock strikes. And so also for n1 and n2 sign bits, this is the actual n1, this 10th bit is the sign bit. So we preserve that as n1 reg 1 here and n2 reg 1 here for the sign bit of n2, and we also preserve whether it is a 0 or the product is 0 or not, and this we will have to propagate at every stage, because this you are going to use only at the fag end. So if you don't, if you forget this statement, naturally the whole system will be a blackout, it won't work, right. So is the case with any statement, even a single statement is missing, nothing will work. So P1 reg 1 etc. means P1 etc., that is what we have seen here, are registered after positive edge of clock 1, clock 2 etc., and so is the case for other clocks which we are going to see shortly. And now in the first stage, what we are going to do is we are taking only LSB, half the total number of partial product, and let us say here what we are doing is this is the very first line of the partial product we had, and we also mentioned that 0 need not be added initially. and because we can straight away put that particular result at the after doing all the addition, that is why 0 does not come here. So, we start with 1 through 6 and P2 is one shift 1 bit shifted left and then only added, and that is what we are doing here. Say we said that in Verilog it is very easy, you do not have to do any shifting operation. What all we had we are doing addition, right within the addition we can do the shifting also without any clock penalty. That is the beauty of this Verilog here. And we are note that one we are taking the very LSB here 0 through 5, total will be 6 bits here, here also 6 bits, and it is equivalent to having P2 is the second one. So, what we have is if you take this P1 number 6 through 1 here, then 0 bit also you assume, and this particular 0 after left shifting it should align with itself with 1. That is the reason why we are aligning 1 and 0 here, and it is equivalent to left shifting by 1, and this is the LSB addition, and this 0 we should not forget to add at the later stage. So, you remember that P1 reg 1 0 bit which has not been accounted here will have to be accounted later on. This LSB is added here, and note the left shifts are taken care, that is what we have described here, and we have S11 through S14 doing precisely the same set of operation, but on different partial products P1 P2 here, P3 P4 5 6 7 8 here. P1 reg 1 0 we have mentioned earlier, etc. will be processed at the clock 2, S11A 6 etc. are the carry bits. So, what we have here, this will be the carry bit resulting from LSB addition. This also we have to take care while adding the MSB. So, with the arrival of the next positive edge of the clock, this is the second pipeline register clock 2, what we do here is store LSB partial sums. We have already evaluated LSB partial sum, and that we need to store here and put it in a pipeline register, and this is how it should propagate. And so, because we have not yet used the result, and which we will be using only later on, and subsequent clock pulse only it will be used, till that you have to keep on propagating, and all this would mean extra chip area naturally, but in, the goal is to speed up the entire operation. We have, this is the price that we are paying for, and similarly here store MSB of partial products, they are all here P1 through P8 here, and this is the MSB here. Note that we have used 6 through 1 there, and we have not yet used 0, and we are now processing the MSB here, and what we are doing is merely registering this in order to process. So, here also you can store 0th bit since it is not yet processed. We have seen that we have not added 0th bit, but we have to register that also, otherwise that will be lost, and we are going to process later on, and similarly the sign also will have to be propagated, also store sign bits and 0 status, that is what is here, right, N1 sign bit, N2 sign bit, and whether N1 or N2 is 0 or the result is 0, that also is propagated. And there is little scope for you to even optimize, you have a look into that and see where you can marginally optimize. I have not taken much trouble in optimizing, probably left it to the synthesis tool, but you can do it and see, find out whether your manual optimization saves any chip area. It will be very marginal, nominal, that is the reason why I did not go into dwell into depths. And here what we are doing here is, so MSB is added here along with carry. So, we had added LSB earlier, now we are adding MSB, but LSB had resulted in a carry. So, that is what we are adding here, that is this here, and once again we are this is the P1 and P2 numbers here, and we saw that in MSB what we had to do is we have also we need to put one more bit here. This may not be really necessary, you experiment with it. I have just put here so as to keep track of the number of bits, for example 10 to 7 here, and whereas in P2 it is 10 to 6. So, we have seen that why it is so, and this 1 bit shift, and so is the case for the other 4 results here. obtained by adding P1, P2 in this stage and then P3, P4, P5, P6 and the last two here. MSBs and LSBs are concatenated here. So, what we do here is, so this is the partial product here, and we have not processed earlier, as I said, 0 bit. So, in the partial product of P1, so we started only with 1, therefore, we should remember it to put that here. So, what we are doing here is merely arranging all MSB, LSB and also the first bit which was not considered earlier, and we have all in the final result of the first stage. What all we have to do is take this MSB, this is the result of MSB, S11B are all part of this, this is MSB we have seen, and that result we need to put on the top first here, and then followed by the LSB result which we had already computed earlier, and this MSB, this LSB we are concatenating here. Concatenating is putting together as a single number, that is this one, and also we should concatenate the last bit we have not processed, which happens to be the very same P1 LSB here, and that is how we get the result of the first stage here. And for the first stage you have 4 such outputs. This is the first stage of addition that we have seen in the diagram earlier for the algorithm, and these are all precisely the same thing here. And in the next clock, that is clock 3, what we do is this is the third pipeline register clock 3, first stage results are stored here for the processing, S11 through S14, these are all the first stage, and we store it in pipeline registers here, and this being clock 3 we give this nomenclature here, and we should once again store the N1 N2 sign as well as the 0 result there here, and this is the second stage, and before the clock strikes we will have to do the evaluation in order to speed up the process, and that is what we do here, and once again we take and process only the LSB here, and that is what we have here. In the second stage what we need to do is we need as I mentioned before, this is the first row of the second stage, and 1 through 0 we are going to left shift the second number, that is why we are having 6 through 0 here. So, instead of 2 you have 0, corresponding thing is 2, that means the S12 is shifted by 2 bits, that is the second stage we have seen in the diagram earlier, and because we have shifted 2 bits, naturally for this 1 and 0, that is 2 bits of the LSB need not be added, and we can merely duplicate that thing later on, and what we need to add is only other than those 2 bits, and here we are adding 7 bits here, and this also naturally 7 bits, and out comes 8 bit result, and this S21A 7 will be the carry bit here, and so is the case for the next result. We have in the second stage 2 results only. In the first stage there were 4 results, and in second stage only 2 results, because 2 numbers are added, 4 of them, and LSB sum second stage is got here. With the arrival of the positive edge of the clock, this is the fourth pipeline register clock 4, and what we do is store bits not yet processed, and these are all the bits not yet processed, especially the MSB we have not processed, and other bits 2 bits we have seen for S11 register we have not processed 10, it was here, say S13 we can see all this here, 10 not used here, and that is what is here, S13 10, so is the case for S11, and MSB also we have not processed, therefore there is no need for you to propagate this through pipeline registers here, and so also the S21A, which is store LSB second stage partial sums. So, LSB we have already computed, and that is the second stage, and that partial sum is also to be stored, and we put it in another pipeline register here, and so is the case for S22A, which is the next output of the second stage. And we also should not forget this N1 and N2 sign bits, as well as the final result is 0 or not. So, what we do is now add second stage MSBs with carry, and what we are doing here is, once again this may or may not be required, you can just experiment here, and for sake of completeness it is there, and probably optimizing tools such as Simplify will do it automatically, and even if you put some extraneous thing. So, do not really bother much about optimizing at your step. And here this is the MSB here, and this is S11, the second stage outputs are S11 and S12, and once again we are doing shift here, because what we are doing is trying to do is only MSB addition. So, same 2 bits shift only is applicable even for the MSB, because it is still part of the second stage, and what we do is we add 2 numbers S11, S12, similarly S1, what is this? This is S11, S12 and S13, S14 are there in the second stage for MSB, and so we need to add with the carry of the LSB, that is what is here, and so out comes these results, and this will be the final sign bit. So, what is being done here, let us have a look. This is MSB and then LSB and then 1 through 0. What we are doing here is what we have done here is we have merely added the MSB, where we did not put it together. So, we need to put them together to form one result, and that is what is here, and that will be 14 through 0 bits, say 15 bits, and this is got from S21 6 bits here, and then S21A another 7 bits, and then finally S11, and these are all the numbers which we have not processed earlier, the LSB 2 bits. So, that is what is here, and this was the LSB result earlier, and this was the MSB result here. And another point, you will notice that we have used 6 through 0, whereas we have used so only here 5 through 0. The reason is this has a duplicate sign bit, a duplicated bit. So, it will not affect the last bit, it always remains at 0. So, when you really take an example and work it out, you will realize this. So, that is the reason why this won't get affected, and in fact we do not have to remove it physically, the synthesis tool will automatically take care, but if you can spot it out, you can do it right in your code itself. That is what I have spotted out here with an example, therefore I just limited to this, right. Otherwise do not worry about that, because synthesis tool will automatically do the optimization. So, what all we are doing here is we are putting the MSB of the second stage addition and LSB of this followed here by concatenating, and also not forgetting the last 2 bits which we have not processed earlier. So, this makes up for the second stage complete result, and result will never affect S21 6 bit, which is always 0, this is what we have already seen. So, just as we had S21, we will have S22 here, and this is precisely same as what we have seen before for the other 2 outputs of the second stage. At clock 5, so far we have seen clock 4, and what happens here, this is the 5th pipeline, and we need to once again store some of these values. For example, S21, S22 are what we have just now processed here, the second stage sum, partial sum, and we also need to store the 0 value or the 2 sign bits, and then process further. So, at this stage, this is the third stage LSB is computed here. So, in this third stage the final output is going to be this, whereas the second stage output, which is this one, is being taken here. In this case what we are doing is, note that we are going to shift for the third stage by 4 bits, that is why 3 through 0 is not being used here, and we need to once again take from 0, this 0 corresponds to 4, because we need to left shift 4 bits, this S22 reg is same as S22, and when you do this one, out comes MSB process here, I am sorry, LSB process here, and which will register when clock 6 arrives. and we also have to when the clock strikes we should also preserve MSB because we have not yet processed, and that is what we are doing here from the previous stage, and put it propagate through some other register here, and in this is third stage LSB, and they are also registered here. So, LSB we have just no process there, and we should once again take care of the 2 sign bits as well as the 0 result registered here. And so, what we had done is so far we have processed the LSB, we need to process MSB here. Once again we use assign statements and process the, and as usual we have put 4 zeros here, although you need not do it, and we take the MSB of first number and MSB of the second number, and as well this is taking care of the shift, 4 bits shift it is taking care, and you can cross check, you can see from here 14 through 12 is 3 bits here, and plus 4 7 bits here, here it is 7 bits here. So, to this we had to add the carry resulting from the LSB addition, which we had done earlier, and that is also to be done without fail, and this will give you the third stage MSB computation, and you have to concatenate all the results put together. We had done earlier LSB computation, and here we are doing the MSB. We had to put them together, that is by concatenation, that is what we are doing here. This one S31B is put here. Once again these 2 bits 6 and 7 will be again zeros, so we are not using that, therefore 5 to 0 we are optimizing by hand right here. And then what we are doing is we put together the MSB this is the MSB results and this is the LSB results, and then what we have here is concatenation of 3 through 0, 4 bits we had not used earlier for S21, and that is what we are concatenating here. So, all this put together will be the final multiplier output here, not yet registered. So, this put MSB, LSB and 3 to 0 bits together, that is what we have done here, and we had to then note that the third stage result will never affect 6 through 5, that is what we have seen here, which is always 0. And with the arrival of the positive edge of the clock, this is the 7th pipeline register at clock 7, we are once again storing all intermediate results, for example sign bits, the 0, and also the results here, this is the result here from the third stage what we had just now computed here. So, this 3-1, this is the 3-1 which we had concatenated MSB, LSB as well as the unused 4 bits earlier. So, S31 is the final result there, and that is what we need to register it, which we will be processing with the arrival of the next clock, and before that we will really work out the do the computation if there is any. Let us see what we are doing here. So, first we said we have been propagating all along this N1 sign bit as well as N2 second number sign bit. So, if you take the exclusive OR, you get the final result. For example, this is exclusive ORing is simple in logic because you know the simple multiplication rules. Say if you multiply plus into plus, you get plus, minus into minus is plus once again, and so long as both these sign bits are same, whether it is plus or minus, the result will be plus. So, if it is one is plus, the other is minus, you get a minus. So, minus is represented as 1 here in binary number. So, 0 is positive. So, when you exclusive OR 2 numbers, for example 0 0 which stands for plus into plus. So, out comes exclusive ORing 0. Similarly, if you exclusive OR 1 and 1, it will be 1 0, you have to drop the carry 1. So, what you get as the result is only 0. So, in this case also minus into minus is plus, and similarly plus into minus, if you put 1 exclusive OR with 0 will give you 1. So, 1 is the final result which will be put here, and that naturally is a minus sign because 1 stands for the sign, 0 stands for the positive number, and that is what we are evaluating here. It is a mere exclusive OR here of the sign bits of the 2 numbers N1 and N2 which we started multiplying. 1 means a negative number and here there is also final result here. We said right in the diagram before, in the partitioning and diagram. So 18 through 0 we have mentioned, that is the final result, which is the product of two numbers n1 and n2, and here we have done the entire algorithm which we had computed using this Verilog code so far handles only the magnitude as mentioned before, and we have just now evaluated the sign of the number. So based upon this sign bit, we will manipulate the final result by reflecting the 2's complement or straight away the number. So for example, if the sign bit is 1, if the final result is 1, that means a negative number, what we had to do is we had to take 2's complement which we have seen earlier, and you can by taking 2's complement of a sign number, you get a magnitude. If you take the 2's complement of the magnitude, you will get the sign number, and not exactly, we had to force the sign bit separately. That is what is being done here by concatenating the last bit to be the 18th bit, we had to force it to 1, because we know at this stage this number is going to be a negative number, because this gives, if it is negative this will be 1, if it is 1 this is a mux realization. So naturally the MSB will have to be 1, that is why we force here. So we need to take the 2's complement in order to get the magnitude. I said incorrectly earlier, sign bit will have to be separately dealt with, and so here what we had to do is just take the 2's complement and of what is this S31? S31 is the actual result here in magnitude form, the entire result 17 through 0. So that is what it is. So you had to take the 2's complement and also append 1 here, that is a sign bit here, and if this is for the negative number, so long as this is 1. If it is 0, that is it is a positive number, result is positive number, what will happen? We have only to just take that S31 which is the result and just add one more bit here, because that was only 18 bits and now the result must be 19 bits. Therefore we append 0 here, implying that this is a positive number. So this is clear here, there is one statement here and another here. So this statement is executed if this is 1, if otherwise this is assigned to this final result, either this is assigned or this is assigned, depending upon the sign bit here. So here we have appended 1 because this is going to be a negative number, and we have appended 0 which is positive number. Either this 1 or this 0 will reflect as reset 18, that is the MSB. So this tells you how we take care of the sign bits as well, and so what we are nearing this completion of this design for the multiplier, and we have seen that it follows exactly the algorithm that we have developed earlier, and so finally we want to register this output and for the DCTQ application, and that is the reason why we have one more positive edge of clock, that is a clock 8, and what we have to do is merely assign this final value which we had just now evaluated, depending upon the sign bit is also taken care. So what we did not take care is whether n1 or n2 is 0. Earlier we had 0 flag propagating all through, implying whether final result is 0 or not. The final result is 0 if n1 or n2 is 0. So that has also propagated, and based upon that one, if it is 1, naturally the result is 0. So we force the result to 0 by this statement, otherwise that is a else statement, assign the same result which we had just now computed using that assign statement RES here. So this is what we have, the actual sign number is available here, that is the usual normal number, whereas if it is a result is 0, you can assign separately. You can also try dispensing with this 0 flag right from beginning. Everywhere you can remove that and find out find any problems. If there is no problem, you can settle with that changed code, otherwise if you find any problem somewhere, you may have to stick on to this again. So I will leave it as an exercise to you. This is the final result, product of two numbers in 2's complement. We started with n1 and n2 signed numbers, one was 11 bits and other was 8 bits. So, out comes 11 plus 8, 19 bits, that is what is here, and 18 is the sign bit here. And this completes the design of the multiplier. And let us have a look at the test bench, and supposing it is 50 megahertz operation, we need 10 here, and we need to include the back connected design file, which is mult 11s into 8s. Of course, for the normal design we do not add this back annotation, and this particular test bench is a module whose name is declared here, and you want only the final result, that is the product, and that is what is listed here. And we declare all the inputs which happen to be simple clock n1 and n2. Although the algorithm is quite complex, the results will be easy to analyze. And we have seen that this is 11 bits, 10th bit being signed, and so is the case with 7, which is also signed. This is 8 bits for n2. And we invoke the design here, mult 11s into 8s. This is the module name. In spite of back annotation, it will be the same, right, because to start with we start only with this name with .v extension for the design, and from that only we get a back annotated file as we have used here, and because we want the final gate delays incorporated, that is the reason why we use the back annotation there. And we have listed all the ports by name here. And once again, to process the actual test patterns, we need to apply different test patterns inputs here, and we start at 0 time. We have an initial, that is a begin and final end will be there. We stagger by few nanoseconds, so that we apply clock only after data stabilizes. That is why we have, instead of 20 here, we need to put 17, so that the data is applied before the clock arrives at 20. That is the implication here. So, in all through the designs you would have noticed this, and the very first inputs are clock has got to be initialized, because we are going to run the clock, and that also to be initialized to 0, and later on the clock will keep on toggling as a positive going pulses, and n1 and n2 are the two numbers we have already seen, 11 and 8 bits respectively. We are forcing them to 0 to start with, and later on every 20 nanosecond, with the exception of this, we change the data, in this case 555 then 5, this corresponds to 0 1 0 1 and so on. Then we apply 2AA, there is no sanctity for each of these numbers, and they are all not an exhaustive test, as we have seen in adder also. You have, if you want, you can do more exhaustive test, you can amend those test benches, but what has been done is all the endpoints and strategic values are checked by this combination, and similarly there is another here, all A's here, and then 7f of 80, a different combination. So, and similarly all this here, and once again I have noted down the paper all this, and all these numbers, and all these are merely test patterns, testing for different input values here, and the last one is 0, then 7f, and they are all hexadecimal. I think the waveform gives both hexadecimal and decimal, if I am right. Let us see what it has in store for us. So, we give some more cushioning for processing further, say by 400 nanosecond or second. This may not be required really, it can be even 100 or even less, and finally stop. This completes the test bench with a final statement of always, wherein you do as usual toggle the clock here, and that is the end module here, and we have simplified results, and before we go into these results, we will look at the waveform here. So, before I zoom, I will just explain what they are. This we have totally we have seen 8 pipeline stages, that is a clock 1 through 8. So, naturally the results will manifest only after 8 clock pulses. Let us first have a look whether it is so. So, here we have a waveform here, and 3, 6, 7, the 8th clock is here, right. So, and because it is back annotated file, and naturally the final result must be delayed a bit here. In fact, there is a cursor marked for the first output here. So, the very first output is, as you see here, is 0 here, and I will zoom it in a minute. And here what we have applied here is, I will just read out different combinations of inputs. For example, as I mentioned before, I have N1 duplicated here. In one case it is in hexadecimal, the lower ones are in hexadecimal, which you can easily compare with the test bench we have just now seen, and corresponding decimal also can be had by using format, which we have seen earlier while looking into the model sim tool, and using which you can have the very same waveform copied here and then format change. That is how I have got it here. So, this is nothing other than this, only in a different format. So, it is very easy to change the format the way you like, and it will be easy for us to deal with decimal numbers rather than the hexadecimal number. You can trust the simulation tool for doing this conversion automatically, and I have verified this to be correct. You can also verify it independently if you wish. And let us see this 0 into 0 must be the 0 here, and that is the result after the 8 pulse which we have already seen. So, this result is correct. So, I have listed here all this. I will read this as well as that, you can have a look. So, the second number is, I will just read out from here and cross check this paper. First is 0 into 0, next is minus 63 into 85, then 682 into minus 86, and minus 1 into minus 128, then minus 683 into minus 1, then minus 1 into minus 127. I am reading from the paper, you cross check on the this. Then minus 683 into minus 127, 682 into minus 127, then minus 1 into 0, and in subsequent waveform you will get some more, and the very first result is 0 here, and that is what is 0 into 0, which is correct. I will zoom this for you to see it clearly. So, that is what we have seen here, 0 into 0, minus 683 to 85, 682 into minus 86, and so on, and this is in hexadecimal and this is in decimal, and the final result is here, and that is available only say after 8 clock pulse. Each clock pulse is a 50 megahertz 20 nanoseconds, so around 160 nanosecond you get the result here, and that is what the result is, 0 here. And if you go into the second waveform, so I will zoom it straight away, and as far as the inputs are concerned, and what we have seen is minus 1 into 0 earlier, that is what here, and minus 1 into, to continue that, minus 1 into 1 plus 127, then 0 into minus 1, 0 into 127. I hope they are there here, yeah, it is there. So, the final results start with 0 here, what you are seeing here, and different results are here. We will cross check with the hand computer thing. First I will zoom this one so that you can see, this is the decimal result here. We will just zoom this. So, you can see here. So, first is 0 result, then minus 58055, then minus 58652, then 128 683 127, and then 86741, minus 86614, then 0, then minus 127, probably it is not there in this. Okay. So, we will see that in the next waveform, and I will zoom it straight away. So, this is basically same, what minus all that we have 0, minus 127 we have seen. Final results are 0 into minus 1, that must be 0, that is what is here, and next one is 0 into 127, that merges with the same 0. So, it is continuing to be 0 here. So, this is the final result we had, and the result was delayed by 8 clock pulses because of 8 levels of pipelining, and this establishes the working of the algorithm. And what we will do is, we will just have a look at the simplified results, what it has to say for this multiplier. This design is mult 11s into 8s, and it works at 125 megahertz here, and this is simplified result, and the device we have selected is the same as what we are going to use for DCT electron, and this gives all the primitive cells usage, and finally it gives number of LUTs for this design. It is rather high for a multiplier, and it is 1%, it is more than the full ladder that we had designed earlier. Of course, the designs are totally different thing, we can't make a comparison, and Xilinx place and route results are here. You see that slice etc. reported there. What is of interest is number of gates. In full ladder we had some 8000 gates here, and here we have just 7000 gates here, and although LUTs are different. So what counts is the gate count, this determines the chip area, and you can go through do the same exercise with other algorithms which you may be learning, say such as VA algorithm, then Booth's algorithm. So many algorithms are there. You can take some of those algorithms and make a comparison with this new algorithm that has been done by this designer, present designer. And here unfortunately the frequency falls after Xilinx and place and route, but still it is quite high, 82 here. And it also creates a bit stream as output for you to load into the actual FPGA in order to test on the hardware, or sell as an IP core if you happen to be an IP core designer. And before we wind up this arithmetic circuit, there is an assignment for you. I will just read it out and explain, and let us see what the assignment says. Code and test for adding two signed numbers of width 16 bits each. We have seen earlier 12 bits. Now I want it to work out for 16 bits, and this time not 8 numbers but just 2 numbers, and each in the following manner. You have to do it in this fashion. Add all the 16 bits at a time without any pipelining. So earlier we had done pipelining in the as far as the data bus width is concerned by taking LSB, and then pipelining functionality as well, and here I want it to do without any pipelining, just add straight away and merely register it if you wish, and find out how much delay it can give, and this is only for 2 numbers here. If you wish, you can do the same thing for 8 numbers and compare the results with the adder that we have already done, and add only, and another way is this is 16 bits at a time. Do the same thing for the 2 numbers addition using 4 bits at a time as well as 8 bits at a time. In fact, there are 3 different problems. This is another problem, this is another problem. You have to solve them independently, and add a pipeline stage, and in this case. So before doing that one, first analyze and use the optimum number of pipeline stages in order to get the best possible speed of implementation. So from the speed point of view, we are doing this partitioning of data bus, say 4 bits or 8 bits or 16 bits, like that, right. So you repeat all this so that you will know where you stand as far as the speed performance is concerned, as well as the chip area is concerned, and which of these 3 designs yields the best performance in terms of speed, chip area. That is what I explained just now. We have a second assignment. In fact, the first assignment is actually 3 for you, and second one is implement test Variagraph code for adding 8 signed numbers. We have done this before, and each of width 14 bits instead of 12 bits we had added earlier. On similar lines, exactly on similar lines, evaluate this, because we are going to use this particular exercise and in our DCTQ algorithm, which I am not going to explain. I am depending upon you for working out for 14 bits, and this is exactly the same thing as what we had designed earlier for 12 bits. That is what it implies here, and each of width 14 bits on similar lines as the 12 bits adder subtractor design shown earlier. Use 6 stages of pipelining. In this case, only difference is we had in the earlier 12 bits addition only 5 lines, 5 stages of pipelining. The final result, the sum came only as an assign statement, and we did not register. But in this case, the final sum will have to be registered case. That means after 5th one, you have to add one more clock after the assign statement for sum. So you add one more register for that pipelining, and add that as a 6th register, and that completes this sum. So, this the one which we are going to use. Similarly, for we will have a multiplier, and that is this the exercise, and which once again is mandatory on you, because we are going to use these register multipliers in our DCTQ register, which I am not going to explain. And so the problem is exactly like the multiplier that we have considered in this lecture. Implement and test Verilog code for multiplying two numbers for the following specifications. N1 is unsigned 8 bit and N2 is signed 8 bit, and N1 is signed 12 bit and N2 is unsigned 8 bit. So, the difference is this is a separate multiplier from this. So, you need to do two independent multipliers. One is 8 bit unsigned, other number is signed 8 bit. This is 8 into 8 multiplier, and one is signed, other is unsigned, and which is signed is also mentioned here. Similarly, we need 12 bit into 8 bit. What we have seen in this lecture is 11 bit and into 8 bit. Here it is different, and this is also different. We need both of this for our video compression algorithm, that is a DCTQ algorithm, which we are going to see later on, and be prepared when we come for that. So, by solving all these assignments, especially this and 14 bit 8 numbers adder, those two are the ones which we are going to use. Use the multiplier algorithm presented earlier. Design each of the above with 8 pipeline stages to increase the speed. Inputs are not registered as usual, as in the case we have seen. So, you see that there are once again 8 pipeline registers here, and take care of this. This is exactly the same as the multiplier presented in this lecture. And we have completed arithmetic. We are going to see design applications later on. Thank you.